vector version of register bypassing. Remember data forwarding or data bypassing? That means whenever the value is available, I pass the value to whomever wants it. For vector register, there's not only one value, not only one single value. There's, say, 64 individual values. So if we want to do value bypassing, should the objects be individual value or the group of values? Of course, individual value would make things more efficient. So when we do the vector register processing, like I load V1 and then use V1, what I can do is whenever individual value is in from the memory, I can pass it directly to the next function unit. Okay? So one value at a time, whenever that value is available, that's the so-called vector element chaining, very similar to the register value forwarding in scalar version designs. We have seen this before. So without vector chaining, we do this. Load all vector register elements in before we start the multiplication, and multiply all the vector elements before we start vector add. With chaining, the latency could be greatly shortened without affecting the correctness of the result. We've seen this last week. And the startup time, finish time, if this is a function unit latency, if this is the time axis, then what we can do is like this: red operation, gray operation, and green operation. And we define something called that time. First vector instruction, then that time, then second version instruction of a second vector instruction. So two components of vector startup penalty include functional unit latency. This is the function unit latency. It needs to read, process, and then write result back. Remember, this is the operation occurring in function unit. This is not an instruction. This is not the instruction. This is the operation occurring in function unit. And that time or recovery time is the time before another vector instruction can start down pipeline. So with this timing, the red one, we will have this that time, and then the green second vector instruction can start. Okay, these are some definitions, and it doesn't have to be so all the time, depending on how capable you are in doing forwarding. Yes?
At the same time there in the first instruction, in another functional unit, something else can be running at the same time as well, right?
Right, if you have many function units. Okay? So it's something like we heard of superscalar. Have we heard of supervector? Many vector operations running simultaneously using different hardware. That's, of course, likely. Okay, I'll skip all these. Not really important. Scatter and gather. Last time I gave you a very brief introduction to scatter and gather. Like you have many independent data items or scalars in memory. In your main memory, you have one piece here, one piece here, one piece here, one piece here. Say you have so many pieces. They're all independent, but you want to operate on them similarly or identically. You want to operate on them identically. So conceptually, you like to treat them as though they were in a vector, right? So how do you do that? The way you do that is first you set up a vector address variable, saying if this is your variable 0, 1, 2, 3, 4, 5, 6, 7, 8. So you say address 0 is where, address 1, address 2, etc. And then you use these addresses to load in these individual variables. So you are doing actually a direct addressing load. So this is a load operation to get him variable 0, variable 1, variable 2, etc. So once you have this, once you have them in the vector form, you can begin to use vector ADD, vector whatever, to speed up your operations and save energy, save instruction bandwidth, instruction decode bandwidth, fetch bandwidth, decode bandwidth, execution bandwidth, and utilize all kinds of vector utilities to speed your process. Later, when you're done, you need to scatter them back. Okay, scatter them back like doing stores. Okay, so this is the so-called gather and then scatter. In between the two, you do vector type operation on these variables, making things more efficient. Okay, so now can you see in the high-level language version what this means? Okay, this is the address of the individual variables. Okay, other than this instruction looks just like a very good candidate for vectorization. Okay, so this is the assembly form. And we should have another example for this. I'm sorry, this is the gather, this is the scatter. So this is the assembly form, okay? And this is the simple, much simpler example. Increment the elements. Maybe I shouldn't say that they are the elements. Increment the individual variables by 1 throughout. Okay, this is yet another example. You have a long vector, but you want to operate only on those elements whose value are greater than 0. Whoops, this means unknown values. You want to operate only on those whose values are greater than 0, but you don't want to do any change on these. Then what should you do? Okay, you use the vector mask register to indicate that the first one you want to operate on it, the second one you do, the third one you don't do, Okay, the vector mask register tells you on which elements in the vector register you want to operate. Okay, so you might have some kind of compare instruction to compare whether this is greater than or equal to 0 to set the mask first. The form of the instruction could be in any form as long as the hardware supports it. Okay, in high-level form, doesn't matter. High-level form can be in any format. Compiler will translate it into machine executable form. Okay. So you understand compiler? Have you taken the course compiler? No, but the reason is that you understand compiler already somehow, right? You all think you know something about the compiler. What is the compiler? What does compiler do? Okay, a little bit about compiler. I have a program written in high-level language, so the statements could be long, could be short, right? The compiler will first do a scan of the program, knowing what characters we have, like the line feed character, carriage return character. Line feed goes to the next line, carriage return goes to the beginning, indicating the beginning of a new line. Okay? Whenever it sees a semicolon, that could be the end of a high-level language statement. So after the scanning, it begins to parse. Parse what? M, A, I, N, space, bracket. Okay, whenever I see M, A, I, N, space, I know, this is a token. And then I check this against my symbol table and found out, this is a reserved word. It should have a special meaning. So after scanning, I begin to do parse. Okay, parse the whole program and then try to understand what it says. Lexical analysis, semantic analysis. After that, I know what the programmer wants, and then I translate it into low-level language program. And in this pass, in the whole process, I do whatever optimization whenever appropriate. So first, I do high level, in other words, targeting at the high-level language program, high-level optimization, intermediate level optimization, and the machine-dependent optimization. So the flow has been very standardized. Most compiler research nowadays target at machine-dependent optimization only. Okay, whenever you have a new machine, new design idea, new pipeline depth, new number of function units, you need to tune the machine-dependent optimization part of your compiler. If you talk to a compiler researcher, he'll talk about computer architecture with you. He talks a lot about computer architecture because he needs to know all the computer architecture features before he can do his job. Okay? So on the other hand, I do compiler research a lot because I know how the new machines look like. Okay, so this is a conditional execution. We need a vector mask register to help us implement this function. Okay, so this could mean clear, I don't know, clear vector mask, and load entire A vector and set bits in mask register where A is greater than 0. This A means the corresponding element in vector A is greater than 0. And then load B vector into A under mask, and then store A back to memory under mask. Okay, so this is a very good code example. Whatever it does, it doesn't matter. It just tells you how to use the mask register. Okay, so for the masked vector instruction, we have masks here. And if this instruction is an add, then I'll add this pair starting from here. I'll add A1 and A2, A4 and I'm sorry, I said that wrong. A1 and B1, A4 and B4, A5 and B5, A7 and B7, and ignore the rest pairs. Okay. Or we can do this. We don't even bother to send those pairs which we don't want to add together to the function unit. We simply send those pairs 1, 4, 5, and 7, 1, 4, 5, and 7 to the function unit to speed the addition up. Compress, expand. So we have seen one example. Here we compress the A and B vectors into shorter form containing only the elements that we want to operate on, and later we need to expand them back to vector C. Okay, the C elements are not produced continuously. Some are skipped. Okay, so we need to expand them back into C. Okay, so here we can see the compress and then expand and then put the result back. This is a load store example. This example corresponds to that pictorial example corresponds to this example. Vector reduction. Reduction is a special term, meaning if I have a vector, I want to sum all the elements together to get the grand total of all the elements. That's the so-called reduction. So what do you think is the most efficient way in doing reduction? With n elements, you do n-1 additions. Yes, that's the very traditional way. But a better way is to do addition in pairs, and then pairs again. Sorry. And then pairs again. With this method, you can have the whole thing done in log n time. Okay, that's what we usually do. Because for vector type machines, the hardware resources are abundant. We assume that we have many function units to do whatever we want. Okay, that's the reduction. Okay, 2003, super vector machine. You can read that on your own. And multimedia extensions. How long can a vector be? Infinite. But how long are vectors usually? Have you seen short vectors? Tell me some short vectors. Very typical example, RGB. This screen is full of very short vectors. This screen is actually a like how many D? One-dimensional, two-dimensional, and RGB, three-dimensional, big structured data. And the last degree of freedom contains only three elements. RGB. Are those very short vectors? Yes, I need to do a lot of RGB type operations. I really don't need very long vector registers, okay? And not very deep pipelined function units. So we do have a lot of short vectors in our daily life. How do we deal with this? Well, maybe we can do simple extension to our designs on instruction set, on hardware, from general purpose instruction set, CPU. Okay, so long time back, about 2 decades back, Sun, Micro, Intel, IBM, MIPS all proposed short vector designs, particularly for multimedia processing. Okay, and the most famous being Intel's MMX. Some people say it's multimedia extension. Some people say it's matrix multiplication extension, whatever. There are 30-something new instructions dealing with very short vectors. And about the vector register, no. I don't provide any new vector register in my x86 CPU. In my x86 CPU, you already have some floating point registers. This is my floating point register file. Each register is already 64 bits long. So MMXs, I simply use these for 4 individual 16-point or 8 individual 8-bit vector elements. Okay, I don't give you anything new. I just use the existing hardware, and my floating point adder can also be modified to do 4 individual element adds as fixed point addition, or 8 individual adds also as fixed point addition. No extra hardware, but can operate on some short fixed point vector values. With this modification, my CPU area, silicon area, could increase by a few percentage points. 2 to 5% area increase only. So MMX is a very efficient, very budget-tight design. Okay. Later, they have MMX2 and SSE, streamed SIMD extension. So we're facing very short vectors. We're facing limited vector register length. Why not modify our existing design to make it capable of handling short vectors? Okay, so that will be the end of this lecture. Any question about vector? Have you heard of something called GPU? GPU, Graphics Processing Unit. GPU is also a very important category of processors nowadays. GPUs have very strong computing power on structured data. Graphics, as you can see, tell me how big is this vector? The whole full screen, how big is it? K times K times a few RGB, sometimes alpha. Alpha meaning transparency. Okay, so for every frame of the picture, of the like motion picture, 30 to 60 frames per second, every frame already has millions of elements times RGB. Okay, very big data. Okay, so we need very special design to deal with it. Billions of objects in the universe, in the space. And I want to show the graph of what I can see from this viewpoint in this direction, in this space. That's the computer graphics. Okay, from graphics to animation and sometimes video, image, somewhat different, but there are some similarities. All requires different processor design, and that's the GPU. That's where the GPU can have its strength. Okay, properties of vector processing. Very quickly, each result is independent of previous result. So we can tolerate long pipeline. Compiler ensures no dependencies, so we can have high clock rate design. So vector instructions access memory with known pattern. We can interleave the memory and use it very efficiently. This can amortize memory latency of over 64 elements. Amortize means memory is very slow. CPU requests data from memory. And remember, for vector processing, usually we don't have a cache for vectors. Okay, cache is of no use to vectors. And how do I access memory? First, I interleave the memory into many modules. And then if this is a time access, when I want to access memory, I request. It responds. I then request. It then responds again. And then I request. And then it responds again. Very time consuming. This will have to repeat for 64 or whatever number of times before I get the whole vector in. If I have only one module. However, if I interleave the memory into 64 modules, what happens becomes this. I request, and then all 64 responses come in at the same time after the same memory latency. Okay, if I do interleaving, if my access pattern is very perfect, then I get this result back after the same memory latency. So interleaving is very smart design for vector type data accesses. And this memory latency can effectively amortized, shared by all 64 elements. Okay, no cache is required. No good at all. It even hurts. And reduces branches and branch problems in pipelines. And single vector instruction implies lots of work. Only one instruction, one fetch, one decode, and then you can do a lot. And then if we compare a RISC design against a vector design, the number of operations for these benchmark programs, all these benchmark programs are not very vectorizable. They're only little vectorizable. So the operation ratio, RISC type versus vector type, will be like 1 point something times. However, the instruction type, the instruction count ratio will be like close to 100 times. You still need to do so much operation. For RISC, you do more branches, right? Because for vector processing, if you have a scalar machine, then you need to use loop to deal with the vector. So you'll have a bunch more branch instructions. But for vector RISC instruction count ratio, one instruction does it all. And here you need to have like 100 times instructions to do the same thing. Okay? Plus, this kind of machine has much higher clock rate. This kind of machine still needs to do all kinds of data dependency checks, structural dependency checks. This kind of machine usually don't have so much burden on those. Very little burden on data dependence check. Remember forwarding circuit design? Yes, no? Okay? Very complicated. Maybe we should have that in the exam. Okay, common vector matrix. I'll leave this to you. Don't need to spend time on it. Whenever I say I'll leave it to you, very likely you won't see it again ever in this semester. No guarantee. No guarantee. Memory operation. For vector accesses, you have heard of stride. For vector memory accesses, the stride value is typically very fixed. Like you do matrix multiplication, you still remember how to do matrix multiplication? How do you get this value? This row times this column, right? Okay, one multiplication at a time. So if in memory your matrix is stored in this fashion, consecutively in memory, then we call this pattern of storage in memory row major, okay? C language uses the row major style. However, if that's row major, then when you access the second element from matrix B, then in memory, there's a long distance from here to here. And this is called the stride is equal to the row size. This is called stride is equal to 1. Okay? Both are very regular, fixed. But this access seems to be more efficient, consecutive elements. These access seem to be less efficient from here to there and to there. Okay? How to make them both efficient? Do you have a way to make both efficient? Have you heard of something like greatest common divisor? Something like that? So maybe you need to have some more modules, a lot more modules. Or maybe you can store this thing in another way, yet another way. Transpose the matrix before you store it. I mean, create yet another transposed version of this matrix. And then the stride will become 1 if you access from the transposed matrix. Okay? So we know this, and we have talked about gather and scatter. And memory design. It can be interleaved into 8 modules. Is 8 a good number? Tell me if 8 is a good number. Depends on what? Don't try to fool me. So if this matrix is 16 by 16, tell me, interleaving memory into 8 modules is good or bad? Terrible. Why? Because your stride, when you want to access the first column, your stride is 16. So you will hit this, and then hit this, and then hit this, and then hit this again. Okay, there's always access conflict. And all these other modules sit there idling. Okay? So usually 2 to the nth modules is a lousy design. How to make it good? I mean, good on average. Use prime number of modules so that your accesses will have much fewer conflicts, or contention, I should say contention, contend for the same module. Okay, so you can see weird design. How come this system uses 7 modules? Is the last one burnt? Okay, 13 modules, unlucky number. Whatever. Okay, so we sometimes use prime number of modules to avoid contentions to the modules. Okay, try all the possibilities and you'll find out prime number of modules is a smart design. Okay, so now you understand why it says bad for 2, 4, 8, 16. Very bad. Okay, how to get full bandwidth for unit stride? In fact, I can let you read these on your own. And for these few pages, I think, here, for this page, I think you should spend some time. Although, looks like a lot of words, but easy to understand. But I won't go through them anymore. Okay, should be easy to understand. And vectors are inexpensive. This is the scalar version. This is the vector version. And they used P0, their laboratory design, for example. So not very trustworthy. I will skip this. Okay, this comparison is not thorough. Vectors, lower power consumption. You should already know why a vector would be a low power design, because fewer instructions to fetch and decode, and a very efficient operation in accessing memory. Like here, whoops, it's gone. For so many memory modules, you in fact only send out 1 address from CPU and can get a bunch of interleaved data back. Okay, only 1 address would do. Okay, usually you send out address and get memory data back, and address, memory data back. The amount of address traffic and data traffic is 1 to 1. But now 1 address gets a bunch of data back. Okay, you saved a lot of bus traffic. Energy efficiency is even worse, because for the superscalar energy, you need to fetch more instructions than you probably need. And then you do branch prediction to do some useless instructions, which will have to be nullified later. okay? And then you have some function units, a number of function units there. Whenever you don't have that many parallel instructions, some function units will sit idle, wasting power, okay? And the control logic for decoding, for comparing, checking dependencies, controlling data forwarding, rolling back for mispredicted branches, all consume a lot of power. That's why we don't even use them in the simpler cores in a multi-core design. Okay. Okay, vector applications, multimedia, standard benchmark kernels, lossy compression, lossless compression, cryptography, speech and handwriting recognition, operating systems networking, databases, and language runtime support, and even for the PC type applications, general purpose applications. We saw some speed up from the benchmarks out of the integer benchmark suite. Okay. Older vector machines to newer vector machines from 76 to 95. And right now, vector machines are not really dying, but the world's top 500 computers, world's top 500 supercomputers are mostly rack type, blade type computers using standard commodity off-the-shelf Intel CPUs or AMD CPUs. Okay. Very quickly, they can assemble a blade, put a bunch of blade in a rack, yes, to constitute a big computer system. While we do have big vectors, but we also have a lot of jobs as long as you attach yourself to the internet. A lot of individual small jobs, okay? So such a design is quick, easy, and can handle different kinds of situations. Design cost is very high. And the time to market for special design is very long. So if you want to design your vector machine, it may be able to be released in 3 to 4 years. But you want to assemble, you see, I say assemble, it doesn't require a lot of special design. If you want to assemble a rack blade type machine, maybe 3 months. Okay. So do we still need very specialized vector machines? Yes, of course, but not in many places. Our Central Weather Bureau used the cluster blade rack type IBM machine to do weather forecast. Many weather bureaus in the world, in other countries, use the same rack blade type machines for vector processing. So let me draw you a picture. This is my rack, a big chassis. This is my blade 1, 2, 3, 4, 5, 6. I may have hundreds of blades. I may have tens of racks. Tell me, can I have some specialized blade? Yes, of course. Okay. All these blades could be maybe 90% are regular Intel i86 32 based cores. but maybe 10% use very special processors for very particular extreme computations. Okay, have you heard of NVIDIA? Forgot how to spell it. No commercial in the classroom. NVIDIA and the Intel Larrabee, a fading machine, and IBM Cell, CELL. Oh, those are the GPU type machines. And we can use those kind of machines to do vector computer or even to do general purpose computing. Okay? Many tricks we can play. Okay, vector summary. Vector is an alternative model for exploiting ILP. If code is vectorizable, then simpler hardware, more energy efficient, and better real-time model than out-of-order machine. Okay, so whether it can be properly vectorizable is very important. And the vector may not be too long, maybe only 10 elements, even 5 elements. For RGB, even only 3 elements. So for the vector machine design, like the Cray says, I have a big vector machine. This vector machine, if you have a program, you can run it in vector mode. You can run it also in scalar mode. Remember, the vector machine also has a scalar part. Okay, so if you run it in vector mode, the vector length could be like vector length, and this is the ratio of vector over scalar. Like scalar mode for vector length of x will be higher than the vector mode. And then later, over this point, the vector mode performance will be much better than the scalar mode. Okay? So the same kind of application, if you run it in vector mode, then this is the so-called crossover point. If the vector length can be over this value, then you should run it in vector mode. Otherwise, you should run it in scalar mode. Do you see what this curve means? The crossover point for Japanese machines is sometimes 100 or so. For Cray machine, it can be as small as 2 to 5. As long as you can get the 2 elements in the vector mode already can break even, can be as fast as the scalar mode. Okay, so American type machine can run short vectors efficiently. Okay, what I have just talked about is the vector versus scalar speed. Minimum size vector faster than scalar loop. Okay, and then when you have long vector, what should you do? When you have short vector, should you process this short vector in scalar mode? That depends on this minimum size vector length. Okay, now back to this diagram again. This is the year. This is the performance relative to a reference machine in log scale. 100, 10, 100,000, and 10,000. Okay, so before 86, we have this kind of speed up. Very suddenly, we get some speed up from 84 to 86. Why? The pipeline design. Okay, and how do we constantly get speed up? Well, the semiconductor technology. Semiconductor technology and some superscalar VLIW out of order type of technologies. And here, this curve begins to flatten out. No more ILP we can exploit. Okay, so from here we begin to see multi-core. Okay, multi-thread starts from maybe here. Multi-threading and multi-core starting from sometime early in this century. And this curve describes only uniprocessor performance. If we describe the CPU, so-called CPU can mean many CPUs inside, no more just one CPU. If we plot the CPU, commercial type CPU curve, then this curve will continue to go up or even tip. Okay, because we're now having multi-core type products. We have seen all these before, right? Do you get any impression? If not, then I won't bother going through it again because you won't get any impression today. Okay, multiprocessors. Why do we need multiprocessors? Because we're facing the growth in data-intensive applications and growing interest in server performance, and increasing desktop performance less important. Okay, desktop performance increase is less and less important because now we have internet, now we have grid computing, now we have cloud computing. Tell me, what's the difference between cloud computing and grid computing? How many of you understand what cloud computing is? Okay, the essence of cloud computing is only one thing. You need to own your own I/O devices and nothing else. Okay, you need compute power. You need to store data, then send it to the cloud. Where the places, where the machines, you don't need to know. It's just like the pipe water. Where's the reservoir of your pipe water company? You don't need to know. All you care is when I turn on the faucet, I should get water out. Okay, for computing, I need to be able to get water in too. Okay, and how much I use, I pay for that part only. So computing storage is become utility-like water, like electricity. Okay, so it's more of a business model. Technically, nothing really new. Okay, but I encourage you to own only I/O devices, but nothing else. I'll provide everything else for you. Come, use my utilities. Okay, most of the time we don't use computer, so we don't need to pay for the depletion, the power, the maintenance, the whatever for my equipment, because I don't need to own them at my home. Okay, it's more like a business model. And in this business model, we need to emphasize some technologies, but nothing is really new. Okay. Okay. Are we through with this page? Almost time to have a break. So, improved understanding in how to use multiprocessor effectively, and advantage of leveraging design investment by replication. Okay, so multiprocessor could be the replication of many uniprocessors plus some interconnection plus some management. Flyn's taxonomy based on number of instruction streams and number of data streams, very simple categorization, single instruction stream, single data stream, multiple instruction stream, multiple data stream, and the other two cases. This is easy. This is like your PC, your antique PC, single instruction, single data. And what about superscalar? Superscalar belongs to which category according to you? Which do you think suits superscalar? VLIW, vector type machine, we have learned all three. Okay, plus the traditional CISC-RISC. CISC-RISC is this type for sure. Vector machine, what do you think about vector machine? Lower left, upper right? Which one? Come on, speak up. Upper right is vector machine. Correct. Bingo. Because you saw this. What about superscalar? You won't be so lucky anymore. MVLIW? Lower right? Wrong. Superscalar MVLIW is still single instruction stream, single data stream. And these systems may include many processors in order to handle multiple instruction streams. And they each can do independent job, or they can do different routines from the same job. Okay, and for this multiple instruction massaging a single data, tell me what kind of machine is that? Like in a classroom, one student, many professors. Tell me what that is. No real example. Some people say maybe pipelining. Okay, because the same piece of data gets processed by stage 1 and then 2 and then 3, but stage 1 and 2 and 3 don't really execute independent instructions. So it looks like this, but there is really no good example. So there is such a category, but not applicable to any real machine yet. Okay, this exploits data level parallelism. This exploits instruction level parallelism. Okay, I should say program level parallelism. Okay, and if I say instruction level parallelism, which category exploits instruction level parallelism? The first one. Right, in here. Still the same instruction stream, but there is some instruction level parallelism. Okay, so that's the superscalar type machine. And the MIMD exploits program level or thread level parallelism. What about data level parallelism? Does it exploit data level parallelism? While independent data sets, correct. But these data sets don't have any regularity, don't have any relationships. So we don't call this kind of data parallelism data level parallelism. We call structured type data. If elements have independence, we call that kind of situation data level parallelism. Okay, so this is the vector type. And this, we don't talk about data level parallelism. MIMD is flexible and cost effective. Back to basics. A parallel computer is a collection of processing elements that cooperate and communicate to solve largest problems fast. Parallel architecture is computer architecture plus communication architecture. And two classes of multiprocessors with respect to memory. Okay, we have a memory system. Processor 0, processor 1, and this is a memory. If all the processors see the same memory, what do I mean by this memory? I mean memory space, usable memory space. If I write to x1 and you read from x1 and you see my value, then that means we use the same memory. Okay, so this, we're talking about virtual memory, user's memory space. If they share this, then it's a centralized memory processor. Okay, or physically distributed memory multiprocessors. Okay. Whoops, this may mean something different. With respect to memory design, first, I have this kind of system. This should be talking about the actual design. We all share the same memory unit. Whether it's interleaved or not, I don't care. Or the design could look like this. I have my memory here. You have your memory there. Okay? And the interconnection could be this. I can access to my memory, and I can also go onto the bus to access your memory. Okay, so this memory may still be shared virtually, but distributed to be attached to each individual processors. So the difference being the distance. I may be accessing the local memory, which is very near to me. Or I may be accessing any of these, which are very far away from me. And these, to me, are with the same distance. Okay, the distance will be the same, whether I'm accessing this or that. Okay, so we call this centralized and distributed. With centralized memory, I cannot have too many processors. However, with the distributed, I can have hundreds or even thousands, the largest being over 64K processors in the system. We did have such a commercialized system in the history. That system is like that big. Okay, 1 meter by 1 meter by 1 meter, 64K processors plus their distributed memory in such a big case. Okay, that processor is called thinking machine. Bandwidth demands can be very high because everybody could be accessing its local memory, right? So the bandwidth can be very high. And for this type of machine, bandwidth has a bottleneck. Okay, although they all must have their own local caches, but there is still bottleneck. Okay, so you understand when the memory is centralized, then everybody will have the same long distance to the memory. However, if the memory is distributed to be attached to each processor, then you may have long or short memory access times. Okay, for different scenarios, you need to design your program differently. If most processors can use it on like local set of data, and these local sets don't overlap a lot, then this may be a better machine configuration. This works all the time with predictable results, but not the best solution. Okay? Okay, centralized memory. Memory can also be modularized. But anyway, the distance from any processor to any memory module is the same. Same distance between any processor-memory pair. Different distances between different memory processor pairs. For the centralized memory multiprocessors, it can be symmetric. By the term symmetric, what do I mean? All the processors have the same computing capability. Like if this is 2 gigahertz Pentium 4, this must also be 2 gigahertz, same version Pentium 4. Same computing capability. Plays the same role. In other words, no one is the master of any others. All are of the same role. And all have the same distance to any memory module. You see, it has to be symmetric in all aspects, not just the memory processor distance relationship. Okay, so when I talked about SMP, this is a very strict term. Everything should be the same. Okay, for SMP system, maybe your program wants a certain processor to be the master. It's okay. It's your decision. Okay, so someone can still play the master's role, but in terms of the hardware, in terms of the configuration, you cannot tell any difference between any two processors or any two memory modules. Okay? Now you understand the definition of SMP? Okay. With this kind of design, usually you need to have large caches, because for the SMP, there will be a likely bottleneck here to the memory. Okay? So you want to have large caches to reduce the traffic bandwidth going through that bottleneck. So usually we do this. And can scale to a few dozen processors only. The number of processors cannot be too large. And although scaling beyond that is technically conceivable, of course I can attach more and more and more and more using a more complicated network like mesh or whatever. But anyway, contention could be very high, particularly the contention to memory module or modules. Okay, so practically you cannot have too many processors. As the number of processors sharing centralized memory increases to a number beyond like 30, 40, then this design becomes unattractive. Okay, distributed memory processor, however, has the reversed pros and cons. The advantage number one is cost-effective way to scale memory bandwidth. Because with this kind of configuration, if your data is allocated smartly near your processor, then there can be much reduced conflicts. So you get this advantage if most accesses are to local memory. And another advantage is reduced latency of local memory accesses. The memory accesses to local memory module can be very fast. And the con is communicating data between processors more complex and must change software to take advantage of increased memory bandwidth. You need to write your program to suit the design, to suit that kind of configuration. Communications. With shared memory, you can use shared memory. You see, I use the same term. With shared memory configuration, you can use shared memory communications protocol. Or you can use message passing. You can use both. Okay, so let's define these two terms first. What do I mean by message passing? I have many processors, P0, P1, and I have memory. Whether centralized or distributed, I don't care. When this processor wants to communicate to that processor, if it says send, then in P1's program, there will be a corresponding statement saying receive. Okay, if you want to send, then there will be a corresponding statement saying receive. And this kind of communication is through buffer. Well, in fact, with buffer or without buffer is okay. Anyway, this message or this piece of data do not need to go through memory. It can go directly from here to there. That's the so-called message passing. Always works. Another is shared memory communication. Shared memory communication says store X and load X. If that's the case, then P0 writes to location X. And then P1 reads from location X. Now, what have you seen could cause trouble so far? First, this statement should be executed before this one does. Okay, but how do they know the time reference? How do they use the same time references? So there must be some kind of semaphore to achieve this goal, okay? Must be some kind of synchronization mechanism. Secondly, my X and your X should map to the same location. In other words, we should share our memory space. Okay, in other words, these two programs are not independent. They should see the same memory space. However, for this one, they don't need to share the same memory space. Okay? Meaning, the red scheme is like this. this is a program. Maybe I put this chunk on P0 and put this chunk on P1. Now, can you see that they're from the same original program? If they're from the same original program, then they have the same memory view. Okay? Okay, so whatever programming style, whatever machine configuration, this always works. However, this works only for situation with these restrictions. Same memory view with synchronization mechanisms. Got it? Which one is better? When you have two processes working together, you always need to share data. Whatever kind of data. Maybe you do half the calculation, I do half the calculation, or maybe this is just a barrier variable. Any kind of data, there must be some kind of sharing. So, being a programmer, if you want to write such an application, would you prefer this kind of communications mechanism, or would you prefer this kind of protocol? Which one would you prefer? Which one? The battle goes on and on between programmers. This one is easy to program, very easy. I write, you read, that's all. Okay, very easy to write. This is more difficult. Okay, but however, if anything should go wrong, this is very easy to debug, and this is very difficult to find the bug. So in the end, I don't know, the battle is still going on. There is no obvious winner so far. Okay?
But I think that also depends on the operating system. I mean, how the operating system assigns which processor, which process to execute.
Yes, but usually the operating system is the big boss, it's in the background. It should be able to support both. Okay, so it still doesn't affect the productivity of the software that much.
But with message processing, you probably need more memory, right?
No, it doesn't need any memory. It just goes right through into the other party. Okay, when you say probably need more, that's not a big concern, because even if I receive this green data from the other side, eventually I need to store it somewhere in the memory. So there's no big difference, not a big concern. Have you done a lot of programming? Try them out. Have you done any parallel cooperative programming? Not yet. Start to learn. This kind of decision will have to be made when we're using the multi-core. Okay, so for the shared memory multiprocessor, if you have a centralized memory, every processor will have the same distance to the memory. So the access time, memory access time is uniform. Or if the memory is, however, distributed, then the memory access time is non-uniform, called UMA, NUMA for short. Okay? If you're concerned about the cache access time, then NUCA, MUCA. Uniform, non-uniform cache accesses. Because sometimes the shared data come directly from the caches, not the memory. So we have NUMA, UMA research traditionally, and in recent years we start to study Uka, nuka. When we talk about SMP, the symmetry comes from shared physical memory. But the sharing of address space could mean distributed memory. So there is some confusion between the two. Make sure you see a very clear picture between the two. Okay, challenges of parallel processing. First challenge is present a program inherently sequential. If you have a program and you want to get 80% speed up from 100 processors, then what fraction of original program can be sequential? 80 times speed up means the sequential part can no more than 1 point something percent. Right? Your execution, sequential execution time divided by 80 is already 1 point something percent. So even the parallelizable portion can be executed in no time. You still can get like less than 80% speed up. Okay, so this is impossible. This is impossible. With the sequential part of being 1%, your idealized speed up will be 100 times only. Okay, so C may be the answer. Second challenge is long latency to remote memory. Now, you found parallelism. You distribute work among the processors, but here comes the problem for shared data. Many processors want to access to this piece of information. Some can use it locally, but the others will have to use it remotely. Suppose 32 CPU, multiprocessor 2 gigahertz, 200 nanosecond remote memory, all local accesses hit memory hierarchy, and the base cycles per instruction is 0.5. So remote access is 400 clock cycles based on this and this. Okay, what is performance impact if 0.2% instructions involve remote accesses? 0.2% times this divided by this, the result is, don't know, you do the calculation and you'll find it out. Okay, application parallelism is primarily via new algorithms that have better parallel performance. You know sorting algorithms. Sorting algorithms, binary sort, sequential sort, bubble sort, many kinds of sorting algorithms. Some can be parallelized, some cannot. So whenever you are given many processors, the first thing you need to do is to choose the right algorithm. The algorithm is at a level even higher than programming, high-level language programming. You need to determine on that first and reduce the possibility of long remote accesses. So being a computer architect, you should try your best to reduce memory latency, and being the programmer, you should try your best to avoid the remote accesses. For example, reduce frequency of remote accesses either by caching shared data, restructuring the data layout to make more accesses local, and today's lecture on hardware to help latency via caches. Okay, symmetric shared memory architecture from multiple boards on a shared bus to multiple processors inside a single chip. So this is a multi-core chip. Plus, we may need many of these chips on many printed circuit boards. Now let's look at this picture. If you have 4 individual cores, how do you assign caches to them? Local cache, local cache, local cache, local cache. Local caches are usually very small, so maybe you need to have another larger cache for the L2 to be shared by all the caches. So private L1 caches share a shared L2 cache in a chip. How many such chips do you have on a PC board? Maybe several. They might share yet another level of cache, L3. Okay? Out from the L2, through the L2 to share the L3. So this is what? This becomes a PC board. PC standing for printed circuit board. How many such boards you have? Maybe tens of these boards in a rack. And every board, or maybe every 4 boards, share a chunk of memory. Okay, maybe 4 of them share a chunk. How many chunks do you have? I don't know. Okay, very complicated design. So you know what I mean by private data and shared data. Private data are better cached in here. Shared data are primarily cached in here or even in here, and sometimes propagate up to here, 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 here. Okay? And caching shared data will cause some problem. If one writes to the shared data, do the others need to know? Depending on your programming paradigm, sometimes yes, sometimes no. Let's assume the more strict case. Yes, all the others need to know. So we need to somehow update or invalidate the other copies of that shared piece of data. Okay, so caching shared data could reduce latency to shared data, yet create coherence problem. Do we all see the same value, get the same version of that variable? Memory bandwidth for shared data and interconnect bandwidth can all be reduced. That's on the good side. But on the dark side, we need to do this. We need to take care of the coherence problem. Now we look at the coherence problem. Suppose location U stores the value 5, and then one processor wants to read U, so the memory sends U to the cache of that processor with the value, current value 5, and the other one also wants to read it. No problem. A read will not generate a new version of that variable. Yet, what if this processor wants to assign a new value to this variable? U becomes 7. Does it know? Not yet. Does it have to know? Sure. Okay. How does it know? U has been updated. What if it wants to use U again? You could get the wrong value if we don't handle things properly. Okay. How to handle things properly? If the other one also wants to first time use the U, does it get U from here? Or does it know U has got a new value? Okay, we need to take care of all these. The simplest way is to broadcast any change to everywhere. Okay? But when you do broadcast, you need to have the medium. Some interconnection doesn't handle broadcast very well. What handles the broadcast the most, the best? You might say bus, but I may not agree with you. Broadcast. What kind of interconnect can handle broadcast the best? What?
Crossbar,
Why?
because it connects everything and it reduces latency. Plus,
Well,
there is no contention for the bus.
It connects everything, but whatever interconnection you use, you'll be able to get to anywhere in the end. So that may not be an advantage. Okay? Bus, very simple, but blocks everything else out, right? Whenever you want to do broadcast. Mesh, crossbar is somewhat not really a mesh. Crossbar is different from mesh. Okay, mesh, binary tree, you always can do some kind of broadcast and leaving some bandwidth for other things. Okay, or better yet, can you do multicast? Do you know what broadcast means? Talk to everybody. Do you know what multicast means? Talk to only those people who need to know. Okay? Can we do multicast to save bandwidth? Yes, that's a better goal, but more complicated to carry out. If you want to do multicast, bus won't work. Even one-to-one communication occupies the bus. Okay? So the best way is to broadcast whenever I have a new value. But when you do broadcast, do you want memory to know it? If you do, then memory is the super slow guy. Everybody waits. And that kind of waiting may be unnecessary. So many things to think about. Okay, let's read through this. Processors may see different values for you after some time. And with write-back caches, write-back cache means I have new value. I'll save it until this variable is going to be replaced. Okay, value is written back only until to memory depends on happenstance of which cache flushes or writes back value when. Okay, when, which, both are unknown, non-deterministic. So write back cache creates even more trouble and unacceptable for programming, and it's frequent. It's very often seen, but it's not acceptable. We need to do something about it. Okay, so like this is processor 1, this is processor 2. A is assigned the value 1 and flag is assigned the value 1 in order. And while flag is equal to 0, print A. Tell me what value will be printed out? Will this print out 1? I don't know. Will it print out the original A value? No telling. Okay? So if you write a program of this kind, then it's very confusing. Okay, whenever flag is no more 1, you print A. Presumably, you should print this out. But in fact, if that's a write-back cache, whoa, this gets replaced first. So memory sees a flag of 1 first. Okay? And when you spin wait on the flag value to change, do you know flag gets a new value? Maybe not. You may never be able to get out. Okay, unless you have some mechanism to update your variables in time. So intuition not guaranteed by coherence. Expect memory to respect order between accesses to different locations issued by a given processor is way too impractical. So to preserve orders among accesses to same location by different processes, we need some design. And coherence is such a design. Coherence, here it says, is not enough because coherence guarantees only single location value can be seen throughout. Okay, so let's go on. Have you heard of another term, consistency? Consistency cares about the read-write relationships among different processes. And coherence cares about, at the same time, all processors should see the same value of a variable. Okay, so somehow it's like the x-axis and the y-axis. Consistency has to do with the ordering. Okay, and the coherence has to do with, at the same time, every member in the party. Okay, so intuitive memory model, reading an address should return the last value written to that address. That's what our intuition tells us. This is easy to guarantee in uniprocessors, but not even when I/O is involved. So we need to academically define what do you mean by this. We developed two terms, coherence and consistency. Coherence defines value returned by a read, and consistency determines when a written value will be returned by a subsequent read. And coherence defines behavior to same location, and consistency defines behavior to other locations. Okay, don't care too much about this. Defining coherent memory system, concentrate on coherence only. Preserve program order, a read by processor P to location X that follows a write by program by P to X with no writes to X by another processor occurring between the write and the read by P always returns a value written by P. Very awkward, even when reading it. Okay, so go home and read it carefully. I'll read it again to you. A read by processor P to location X that follows a write by P to X. Okay, so P writes to X first and read from X next. If there is no write of X by another processor occurring between the write and read by P, then the value returned by P should always be the one written by P. Coherent view of memory. Read by a processor to location X that follows a write by another processor to X returns the written value if the read and write are sufficiently separated in time and no other writes to X occur between the two accesses. This has to do with consistency. This has to do with coherence. Coherence says whenever you write, that write should be reflected to all the other members. Write serialization that has to do with consistency. Again, two writes to same location X by any two processors are seen in the same order by all processors. Things will become more clear and easier when we talk about coherence. If you are somehow confused, don't worry too much. Consistency is taught in the OS course more than in the computer architecture course. So I'll not cover consistency in a great depth here. Okay? However, coherence is somehow unique to computer architecture course. So coherence will be covered to a great depth. Let's start from here. Write consistency. No, I'll skip the consistency. I'll go to the coherence directly. Okay, program on multiple processors will normally have copies of the same data in several caches. Okay, still remember this diagram? Many caches may be caching the same variable. Now I'm going to give you a much simpler diagram. Processor 0 with its data cache, 1 with its data cache, 2 with its data cache, and then memory. We look only at this. Rather than trying to avoid sharing in software, symmetric multiprocessors use a hardware protocol to maintain coherent caches. So, if this cache holds the variable X, let me be more specific. In the beginning, no one has X. If P0 reads X, then X goes into P0, and we call X being in the shared state. X is shared by P0. Is there anything else sharing X? Not yet. But the status of X is shared or shareable. Maybe shareable is easier for you to understand. Later, P1 wants to read X. It sends out a message saying, I want X. Okay, this message goes on to the bus. Now, the key point is everybody should watch the bus. So P0 knows that P1 is reading X. If P1 is reading X, does P0 care? No, because P0 says X is shareable. So anybody else wants it, get it. I don't care. Okay, so P1 can read X in and mark X as being shared also. Later, P2 wants to write to X, okay? So the write X signal is also sent on to the bus. Does P0 see this signal? Yes, P0 knows someone wants to write it. If someone wants to write it, X will get a new value, so my version is no more good. So whenever P0 sees it, P0 should invalidate its X in its cache. P1 should do the same. And P2, since it's going to write to X, it will say X is owned here. Or most people use another term called exclusive. Exclusive means I'm the only one who can have it. You cannot. Okay? And once it's exclusive, X in memory is also no more good. Okay? So later, if P0 wants to read X, tell me what happens. The signal is sent out to the bus. Does the memory see it? Yes, the memory sees the signal, read X. Does the memory know that X is no more good? Does the memory know its X is no more good? Yes or no? No way it can tell whether the X is good or not. Okay, it doesn't know. Luckily enough, does P2 see this signal? Yes, so P2 sees the read and it will send out a signal saying, hey, memory, don't move. Or it will say, ignore memory, listen to my reply. I'll give you the X value. So P0 gets the X value. Does P2 have the X value? Yes, but now it's no more exclusive for itself. So you will have to change this to shared 2. Okay, so now you see how the broadcast works. Always telling people what kind of variable, shared, exclusive do I have? Okay? So the way we introduce this protocol to you is like this. Every cache line, this is a cache line. Cache line is marked invalid or shared or exclusive in the caches. So this cache line could be invalid in memory, but there's no place for memory to mark the status of a cache line. Okay? So memory is passive. It just does nothing. It just does whatever it did previously. Okay? But in the caches, every cache line will have to be marked, the state of it. And invalid actually means it doesn't exist in the cache. So there's really no such a state. It's just for the illustration purposes. Okay? In fact, in the cache, no way you can mark cache line as being invalid. It just doesn't exist in the cache. Got it? Okay? So whichever cache line you have, it will have to be in the shared or exclusive state. And every time you want to touch on any cache line, you need to let anybody else know. Very simple protocol. Okay, Yes.
So how does the processor know that cache line is invalid?
If it doesn't find it, then it's invalid. It doesn't exist. It just completely nothing there. Okay, but it's for easy explanation purposes only. Okay, so now you see, sometimes I need to do migration. When I have an exclusive version, I need to migrate it to the other place and to duplicate it in other processors. Okay, so whenever you want to use your local data, as long as they are in this state, you can read as you want. Whenever it's in this state, you can read and write as you want. Okay, and if you want to write, can you write to shared? Can you write to your shared cache line? Yes or not? Of course, yes. If you want to write, who can stop you? But you need to stop the others. You need to tell the others, hey, I'm going to have it exclusively. Invalidate your version first before you can write. Okay? Okay, so you see, everybody will have to watch what's going on the outside world. So that's Snoop. You know Charlie Brown and Snoopy? You know what Snoop means? Always sit on the bus. Always have to know what's going on the outside world. Okay, so you always broadcast whatever you're doing to let the others know what's going on. Always broadcast, always broadcast. Okay? Well, a better protocol will broadcast only the necessary message. Like if you're reading to a shared data, you don't need to let the others know. So now you don't broadcast. Okay? But if it's a cache miss, you need to let all the others know. If you want to do write, maybe you want to let all the others know. But however, if you are writing to your exclusive cache line, you don't need to tell the others. It all happens inside of you, and it's good enough. Okay, so broadcast whenever absolutely necessary.
So in the end, basically the speed overall of the whole system will depend on the bandwidth of the bus bandwidth between the caches.
I don't know. Because different applications will have different work type breakdown. But you may be right. Very easily, the broadcast medium is the bottleneck. Very easily it is, but it's not always guaranteed. Okay. As I told you, a good design should have bottlenecks everywhere. In other words, the system is balanced. Okay, so that's the Snoopy type coherence protocol. Let's skip this. I'll come back to it later. Let's see the protocol. Okay, this is the protocol. It uses the write back, the most preferred write policy these days. So whenever CPU wants to use a variable which is not in its cache, it will encounter a cache miss, right? So the CPU will send out a read signal to the bus and somehow get this cache line back and put it in the shared state. From then on, no matter how many inside reads you want to have, you always do it internally and keep the cache line in the shared state. So you see CPU something, CPU something. These mean the internal activities. Like for instance, if you want to write to this variable, you have to place a write miss on bus and then write it. After you write it, you have a new value. The others will know they don't have the most recent version anymore by seeing your write miss signal on bus. Others know they should invalidate their version, right? Why don't you say write inside signal on bus? It is a write hit, right? It is a write hit inside. Why do you place write miss signal on bus? But why don't you say write hit? Well, because this signal is readily available. And this signal will cause the same effect. We don't need to add another control signal to the bus. Okay? A write miss will cause the same result that you want. Okay? So you may say, hey, it's not a write miss. But I'm telling you, hey, why don't you use the existing signal to serve this purpose? Okay, so as long as you're in exclusive state, you can do as many reads or writes internally without having to send out any signal. Okay, so if you're in the invalid state and this time you want to do a write, also you place write miss on bus, and this write miss is the write signal to send out. This write miss is only a replacement signal which will cause the same effect. Okay, so this is a true write miss. This is a fake write miss. Then you enter into the exclusive state. Okay, so now you see. Now do you know how to read this state diagram? Okay, you should be able to explain every transaction on this diagram. Is it easy? This is what you do to broadcast. What if you see something on the bus? Like if you're in the shared state, and if you see a write miss on the bus, no, we don't have that. We should have that. If you're in this state, and if you should see a write miss on the bus from the outside, then you should hurriedly go to the invalid state. See how it works? And see, this diagram is not complete yet. Okay. Get the idea? Okay, let's go back a little bit. This is a similar diagram, but this diagram has only valid and invalid states for the caches. So tell me, how many states can we have? Invalid, shared, exclusive. How many states should we have? How many states can we have? The answer is at least 2 states, valid and invalid, but as many as you want, I don't care. As long as you can show that your protocol, your design is better than the others. I've seen 4-state designs. I've seen 5-state designs. Okay. Yes? It is not synchronization mechanism because all the processors are running freely. So some might go faster, some might encounter some cache misses, long latency, and lag behind. Yes. That's for heavily dependent data. Here, we don't mean that. Okay? Like, do you have a girlfriend? You want to date her tonight? And you want to date her before the dinner or after the dinner, or you don't care, you just want a short chat? Okay, if you want to dine together, then you need to synchronize. Or if you just want to have a few minutes chat, you don't need to synchronize. You see different needs, different ways of solving problem. Got it?
Yes, because my
if you have some kind of barrier. But here, we don't talk about that. You could have those, you don't need to have those. This is a general solution. We don't talk about the barriers. We don't talk about synchronization. Okay? Okay, broadcast. Maybe I'm the only one using this variable. They don't need it at all. So all the broadcasts waste bandwidth. Plus, if I have hundreds of these, then very quickly, the bus will be saturated. How do you deal with that? We're talking about 1,000-core multi-core processors. How do you deal with that? Another thought is like this. I don't care what interconnection you have in here, but now I do something differently. For the memory, for every cache line, I expand some fields, attach some fields to it. Okay, this, as you know, the DRAM design don't have any extra room for these notations. But I can use another DRAM to build a table for that purpose. Okay, so for every cache line in my memory, I will mark like I have so many processors. Oh, this cache line has been read by this one, by this one, by this one, by this one. I know exactly who has what. Okay, I have such a table telling me who has what exactly. Okay, so whenever someone wants to write, okay, I know I need to go to A, C, D to invalidate their lines. So here I'm not broadcasting. I'm using a rifle to shoot A, C, D. Pew, pew, pew. You three are dead. Okay? To save broadcast traffic. With this, I can use some kind of point-to-point interconnection. And point-to-point interconnection can allow more message to coexist in the network, right? I don't need to waste any message in my interconnection network. With this kind of design, you see what this is. This is a directory. It tells me everything. I look the directory up and know what to do. Exactly, no waste. Okay? So remember I say, I'll get back to the directory. Now I am. Okay? So with the directory, no broadcast, no message flooding, but with a new problem. The directory becomes the new bottleneck. How do you deal with this? Interleave it. How do you deal with this? Also let the local cache lines copy its state such that if there is no necessity, you don't need to tell the directory what's happening in you. Like for shared, if you're reading to the shared, you don't need to tell the directory, hey, something has gone. Okay? So now you understand what's Snoopy? Everybody knows everything going on. What is directory? Only when you're concerned, I'll knock on your door. Okay? You don't need to listen all the time. I'll come and knock. Got the idea? We're 7 minutes past the time. So, question. If no question, then see you in the quiz. Yes? Up to this point. Any other question? Okay, we'll have quiz next week and we'll lecture on the 6th. And then we also have one group presenting.